My talk is going to be much more mathematical. So this is a joint work that we have with a team of people. Some of them are in the room right now, and they will uh, they came to us in combinatorics in mathematics with a question, with a very concrete question, and we did something in a mix between having some physical motivation, and then we ended up doing some discrete mathematics. And I'm going to just give you a broad overview of what we did. So we call it convex N-Representability. And so to go to the point, there may be, so my background is more in mathematics, so some of the language may be a little different. So let me just review everything that that we do in this in plain language, or at least in language that I will explain from zero. So we are always dealing with Hilbert spaces that in this project, everything is finite dimension. Maybe I forgot to say it here, but we are going to, even if something is infinite dimension, in order to compute, we can do a finite approximation. For us, everything is finite dimensional. And we are going to be dealing with Hermitian operators. I use the symbol E, and they form a real vector space. So that's some terminology. We also have the group of unitary operators and the space of density operator. So a density operator, just to reiterate something that people know here, and it's been defined basically in every talk, but we say that is positive. One way of defining it is to say positive definite and trace equal to 1. And this will be the definition of a density operator. And a common theme is that sometimes this is some definitions are unitary invariant. And when something is unitary invariant, is stable under the conjugation of the unitary group. To be more precise, we can give a spectral characterization. So instead of talking about operators, we can simply talk about a bunch of real numbers. And a spectral characterization of these density operators, simply that the eigenvalues are non-negative and they add equal to 1. Okay. All right. So more terminology, H1 will be just one particle. And again, everything is finite. So we can think of this as being the complex numbers to the D power. And then we can also take the wedge product of this, and this will be indistinguishable antisymmetric particles. Mathematically, you can do more things here. And I say this because it's the most, to have one example in mind, but we can also do the symmetric power. We will be dealing with bosons. And that's the level of generality that we work in the paper. So we're going to be focusing on mostly on fermions, but we also have some results for bosons. And the theory mathematically is pretty much the same or very similar. And even though we are putting a D here, the idea is that whatever we do, it has to be stable. So we need to be able to let D go to infinity somehow. So, all right, we hopefully we will not have restrictions that heavily depend on D. D is supposed to be 100, a million, and eventually infinity. And hopefully the descriptions of what we're going to do, they don't depend too much. Hopefully there are no constants depending on D. Okay, so there is a map, the partial threshold. You know, this is the reduce in the R of the workshop. So now we have all density operators with acting on n particles, and we take a reduction. So people call it the marginal or the partial trace, and we now get a density operator acting on one particle, as you well know. So this, for example, the image of this is unitary invariant, and we would like to just give characterization of the image. Because it's unitary invariant, we can do a spectral characterization. And this spectral characterization has been known for a while. So Coleman in the 60s gave a spectral characterization basically saying that this thing about the hypersimplex is not important. What in concrete terms, this means that each eigenvalue has to be between 0 and 1 over n, and the total sum is equal to 1. This is a good characterization in the sense that D is not involved. Obviously, it is involved because you have D terms, but the description makes sense with 100 or a million or infinitely many. All we need is that each eigenvalue to be between 0 and 1 over n. Some people normalize it to be between 0 and 1, but yeah. So this is the solution to which operators are reduced operators. Okay, but now we want to do something more specific. So this is very general. So I just take any density operator, I reduce it, and I can characterize that big set. But now we want to be more specific. So this is where the W ensembles comes into play. But again, let me define all of the language that I'm going to use in case it's different from what is used in physics. So we focus on density operators, but I'm going to fix the spectrum to be given. So the spectrum in principle will be a set, but we can think of the set to be it's a bunch of real numbers. So I can order them decreasingly, or at least weakly decreasing, and it becomes a vector W. So I focus on this set of density operators with a given spectrum. Mathematically, this has a lot of structure, and people have exploited this structure. This set is non-convex, it's a whole unitary orbit. This is almost by definition. If I'm saying that all of them, I'm asking for all of them with a given spectrum, the unitary group acts by conjugation. It doesn't change the spectrum. And in fact, you can, any two operators with the same spectrum will be connected by are conjugate to each other. So this is a unitary orbit. And because of this, this has more structure that I'm not going to get into detail, but this has something called a symplectic structure. This matters for some people, but not for us. So we can skip this. And now we are going to take the reduced operators or marginals. Again, everything is unitary invariant here, which is a big difference, because if you take the two reduced density operators, if you take the partial trace to two factors, it will no longer be unitary invariant. And that's one big difference. That's one big difference. So in this case, we land into something that is unitary invariant. So we can give a spectral characterization. So we can say when, it will depend on W, but when a given spectrum is going to be in the image of this thing. Okay, so again, we are reducing ensembles, or in mathematical terms, we are reducing operators acting in N particles. We are fixing W. So W is W is the spectrum, and we take the reduction. And now we want to see what operators do we get. Not only that, I only care about the spectrum of the operators that we get. And the spectrum usually, normally it's just a set, but we can order decreasingly and it will become a vector. So we are looking at a vector, we are looking at elements of, and these are real vectors. So we are looking at a subset of Rn for some n, Rd in this case, actually. So this problem, the previous one was solved by Coleman in the 60s. This problem is also mathematically at least solved. So there is a theoretical description on what are all possible spectra that we can get from a reduced density operator. And maybe surprisingly, these spectra, ordered decreasingly, they form a convex set. Not clear a priori why this thing is convex. And not just that, but it has finitely many extremal points. So that's what we call a polytope. And this, to study this object, is complicated. Mathematically, there is a very interesting solution, but the dependence on D and how to describe this set becomes complicated, because this thing is convex. We can describe it with the extremal points or with some linear inequalities, but to obtain these linear inequalities in practice is complicated. So this is this solution it builds into the work of a lot of people. If we want to do this precise density with a given spectrum, I reduce it and then I take all possible spectra. This is a long story. Essentially, this is a heavy result by Bernstein and Shamar. And the polytopality of this, so the keyword is moment map. This is related to the symplectic structure. And this proof builds onto the work of a lot of people. So this can be traced back. So one of the convexity is due to Francis Kirwan. And this was building on a long series of papers that start with generalizing constant and even something called the Schur-Horn theorem. So this is like 100 years of people adding a little bit to it. This is theoretically interesting, but in practice it's complicated. So we're going to take a relaxation. So the relaxation that we propose is the following. So the set of all density operators with a given spectrum W is mathematically interesting, but one thing that it is not is that it's not convex. So we just take the convex hull. Now the convex hull where? these operators, I mean, operators on a complex vector space, they form a complex vector space. So we need to remember that we have to take a convex hull in a real vector space where we have inner product, but that makes sense. We can restrict to the space of all Hermitian operators. That's a real vector space. Everything is finite dimension. So it makes sense to take convex hull. So this thing, it's complicated. I'll give you a cartoon in a second. But now we take the convex hull and now we have something convex. When we reduce it, we get something that is easier to prove that is convex. And now our set became bigger, right? We are relaxing this problem. Now we are catching more. This is bigger than simply the density operator with spectrum W. This is bigger than that, but now it's convex. It's easier to work with this. And we study the image. What happened? Wait, some problem. Wait, give me a second. There is a problem with the slides. Nothing else after this. Wait a moment. Give me a second.
You are muted, Federico.
Okay, sorry about that. I don't know what went wrong with the slides. Oh, can you see the pictures?
Yes.
Yes. Okay. Okay. Sorry about that. So we were talking about a relaxation, and instead of looking at the operators with a fixed spectrum W, now we are taking the convex hull inside the space of all Hermitian matrices. This is a slightly bigger, but now we can study. We have more tools to study this thing, and this is what we are going to do. We're going to compute the image of this thing, and this image is also convex, and it has also finitely many extremal points. So it's also a polytope. It's a discrete, it's something discrete. And to prove that this thing is a polytope and that is convex and all of that, our tools are much simpler. We basically use this GOC method, cross-Olivera-Con, optimization problem, and everything is, we use much less technology, and we are able to, at least from the theoretical point of view, this is a relaxation, but our proofs are simpler. And also we can not just on the theoretical side, but on the practical side, now we can compute more. So this is more or less the cartoon of what we have. This is the polytope what we were looking for, the green leaf. So this is really, that's the honest solution. So this will be all reduced operators of coming from a W density matrix. That green petal, this thing, when that's what happens when you order the spectrum decreasingly. If we take, So in this picture, all of these petals will be all possible orderings of the spectrum, and this will be like the petals of this flower. Now, what we say is that we are catching something slightly bigger. So what we catch something bigger, but again, we can keep it to describe all of the spectrum decreasingly, or at least weakly decreasing. So we got something bigger, which is the blue part of this. So even though we have something that is bigger, it is still meaningful, because all of the inequalities that we catch, you can see these inequalities here in this cartoon, but also something similar will happen. They are valid in the petal, and when we have something that is facet defining, when we really touch the blue region, we are also touching the green region. So these inequalities that we get are non-trivial, and they are like relevant. They are, how do you say, they do not simply follow from the Pauli exclusion principle in the green petal. So what we are finding are necessary but not sufficient conditions to describe the one reduced density operators. Okay, and also we can argue that in practice, we are close to the boundary, because by Pauli exclusion principle, you are as close to be like the position to be 0, 1. So we are in this cartoon, what we are capturing are the inequalities that are like the farthest away from this will be all of them being equal. So all of these things are mathematically relevant, but physically we argue that these extremal ones are the most important ones, and we can compute some of them. Not all of them, the sheer number of them is just too much, but we can compute some of that. And in our computations, we can do a small model for n small, the number of particles. B can be like something small just to compute. And then we can let d goes to infinity while keeping n fixed. Okay, so this is what we are, this is the end result. We are capturing something slightly larger, but at least we can give concrete inequalities for this. Again, because this is a convex set in a polytope, so with finitely many extremal points, we can describe it in two ways, either by giving the extremal points, and that we can do, it's not super helpful. What we really want in an optimization problem is a bunch of inequalities to test membership quickly. We need to be able to test whether a given spectrum is possible or not. And this will be done by checking finitely many inequalities. Okay, so this is what we do. Now, let me tell you briefly, without going into a lot of details, how this thing goes. Everything, so we've seen functionals and derivatives and a lot of things, but here, everything becomes discrete. So it's a little unexpected for us that it all becomes about combinatorics. And this is where we develop some of this theory. But just to do one example of more or less what are we doing. First, we justify that some of these extremal points. So how do we get these extremal points? Well, roughly speaking, the idea is that we have something like this. So we have, let's say, d equals 8 and 4 particles. And these particles are fermions, so they cannot all be in the same place. In my head, d is just the number of like boxes, and I have 4 balls, and they cannot be on the same box. And now they have some weight, which may be energy or maybe something else, but let me call them weight. So I put some weights in the boxes, and I just have to start counting in for each box configuration, what is the weight of that thing. And I want to order them from the smallest to the largest one. Now, we start exploiting certain things in this particular problem, which is symmetry. By symmetry, the boxes are more or less the same to me. So I'm going to assume some order from that is the smallest one to the largest one. And now I put 4 balls in all possible ways. Those are the configurations. And each configuration has a weight, and I simply order them. So if they are really increasing, I know for a fact that the smallest one has to be in the 4 smallest one. But which one can be the second smallest one? Well, there is only one choice, 1, 2, 3, like the 3 smallest ones, and you jump 1. But then things get a little more complicated. Then who could be the third smallest one, and so on. So this picture that I'm doing here is just keeping track that if these guys are ordered this way, I know for a fact that 1, 2, 4, 5 has to be smaller than 1, 3, 4, 6. So when I'm ordering them, no matter what, this has to come first. So I need to start doing like a chain here and ordering, but that ordering has to respect this partial order set that we define. Which orderings are possible? Now it becomes a discrete question, because you cannot just simply, it's not true that any ordering that respect this partial order will be realizable. It's not, sometimes it's not possible to find weights that the given ordering is induced by the weights. And just finding out which orderings are possible is a complicated problem. Like, some of them are not possible, and it's kind of mysterious why they are not possible, or how to enumerate them or something. What we do in practice, when we need to do all of these things, we use like some dynamic programming method in which we know that this is the first one, we know that this is the second one, and if we know the first 5, then this will give us the possibilities for the sixth one, and we test each of them, and then we start growing the tree. So we start growing the tree of possibilities from the bottom to the top, and this is efficient. And we really have to do this. There is no way to skip this, because a priori it's very hard to know whether an ordering is possible or not. So what do we do with these orderings? Taking each of these orderings, we combine that all of these, we have a recipe to go from these orderings. We have some vectors that record the positions. We combine them to get another vector. And these vectors that we get are vertices of a polytope. I say polytope and all of this because we do it in general, but you can think of this in the previous case. So just positions there are vectors indicating which 4 positions I'm taking. When I have an ordering, I combine them somehow and I get a vertex. Now, that's not what we want. We want the inequalities. So we have to be more careful with this and develop more theory, but we can do it in an algorithmic way at least. And when we start with something called the hypersimplex, we get the space of all. I'm missing a bar here. The convex hull of the reduced density operators, but the convex relaxation. And let me just run to you quickly through an example. Sometimes we don't want to order all of the possibilities because they are too many. We only care about the lowest, let's say 4. So let's say that we only care about the lowest 4. So we will have to consider, first of all possible orderings. Now, all possible orderings, only the first 4 positions, let's say that we are in boson. So now they can accumulate. So the smallest one is, I put 3 of them in the smallest one. So 1, 1, 1. Then the second smallest one will be 1, 1, 2, and so on. So we have only 4 possibilities. And with those 4 possibilities, what I'm saying is that we somehow create vertices of a polygon. And let me just show you a picture. So we were using symmetry by saying, well, they are ordered in some way, but we have to consider all possible orderings. So this thing has a symmetric, in this case, I can permute the weights of the boxes, and we will get something like this. So we get the 4 ones that we found, but up to symmetry, we get this whole thing. And that's not what we want. We want inequalities. So we do some other tricks to get the inequalities, and the inequalities will look like this. The inequalities, they look, I mean, there have to be a lot of them, but now we use a trick. We just put X decreasing. So this is a way to say the space, because everything is very symmetric. So for any vector, we order the entries in descending order. For example, this line saying that the first one, but in descending order, this inequality is saying that the largest one is at most something that depends on W. And this is really hiding for the largest one to be smaller than something. All of them has to be smaller than that. So there are a lot of inequalities here, but we can compactly describe them like this. And only the right-hand side depend on W, and this is some stuff that we can compute. So this will be something that we care about. And again, we argue that, look, that most of the polytope remains there. So most of the possibilities are like inside. But the argument is that in the physical situations, or we study physical situations in which we are as close to the boundary as possible, where these new inequalities become relevant. So at the end of the day, that's what we do. That was a small example. So we have like a in this case, a shortcut that we were taking is that we didn't order all of them. So we didn't care about all energy levels, only the smallest, in this case, 4. So if we focus on the lowest energy levels, and we can do it all the way up to 13. Not for, I mean, that computationally we can go up to 13. If needed, we can go further, although not much further. I think that we have a hard limit at around 20. And we can describe the possible spectra of reduced density operators and if we only care about the smallest energy levels. And the good thing about this is that first of all, it's concrete, and second of all, we can also give a recipe, it's not too complicated, to for each of these inequalities, we can raise the parameters as much as possible. So we can make D as large as possible, and we will get these inequalities to be valid. We are going to miss the whole object. So we are producing valid, we are producing necessary, non-trivial necessary conditions, and necessary but not sufficient. That's the only thing to keep in mind. And they are non-trivial. They do not follow, in the case of fermions, they do not simply follow from Pauli exclusion principle. So these are the generalized exclusion principles. And also we do something similar for bosons, even though there is no Pauli exclusion principle there, but there are some linear restrictions on that case too.
1 minute.
And that's all I wanted to say.
Okay, thank you very much for the presentation.